I hope we're doing good. I hope we're happy and safe in our homes. Um, this is lecture number 13 with your host, Professor Phil Pinzoni. And in this lecture, we're going to be focusing on spatial variation in vegetation patterns. Now, there's three parts of this lecture. Number one is we're going to focus on topography and how these topographic influences have a interaction with these vegetation patterns. Number two is how soil influences vegetation patterns. And then number three is the emergent landscape, which is actually the integration of these interactions of topography, soils, as well as disturbances. So, what we're actually seeing in these ecosystems is a remnant of all of these influences. So, we're going to then focus on this emergent landscape. So, we're actually going to look at 4 ways topography influences vegetation type. The first way we're going to look at is elevation. As you increase in elevation, temperature decreases. This is something that we clearly have understood from an early age, but we need to actually know why. And we're going to talk in terms of lapse rates. So if you look at the picture on the right, these are parcels of air, and each parcel, as it moves up in elevation, the molecules get further and further apart. This has to do with decreasing pressure. So there's more atmosphere pushing on this parcel in lower elevations. Again, when that parcel moves up, there's less atmosphere pushing those molecules together. The further away these molecules are, the less they're colliding, the slower they're moving, and the cooler those parcels are. So we need to better understand what a lapse rate is. We have to know the difference between wet versus dry adiabatic lapse rate. So this term, adiabatic lapse rate, is the focus on this slide. So if the parcel of air rises and remains dry, it will cool at what is known as the dry adiabatic lapse rate. Now this adiabatic lapse rate, this dry adiabatic lapse rate, is equal to 5.5 degrees Fahrenheit per 1,000 feet. Relatedly, if this parcel of air sinks and remains dry, then the parcel of air will increase in temperature at 5.5 degrees Fahrenheit every 1,000 feet. So if we actually apply this to a real life example, the Sierra Nevada mountains are 14,000 feet from the Pacific Ocean in California, and the parcel of air moving, if it were to stay dry up this 14,000 feet elevation, would decrease by a total of 77 degrees Fahrenheit. Now, on the opposite side of the mountain, if that parcel of air moves over the top and it still remains dry, it will increase by 77 degrees Fahrenheit as it descends that 14,000 feet. However, cooling causes condensation of water molecules. So water is in a gaseous state until it cools enough and reaches its dew point. Condensation then occurs. So once condensation occurs, that parcel of air that is rising is then saturated with liquid water. When a parcel of air is saturated with liquid water, the properties of that parcel is changed. So the parcel will actually cool at a slower rate as it's increasing in elevation once condensation occurs. We refer to this as the wet adiabatic lapse rate. In the wet adiabatic lapse rate, the parcel of air cools as it ascends in elevation by 2.7 degrees Fahrenheit for every 1,000 feet. So if this parcel of air was cooling at the wet adiabatic lapse rate for those 14,000 feet, that parcel would only decrease by 37.8 degrees. So stark differences between wet and dry adiabatic lapse rates. These properties are totally different in either of these lapse rates because the latent heat of condensation results in the atmosphere gaining energy when water vapor becomes liquid water. This condensation of vapor is important because it creates clouds, which then release precipitation, both rain and snow, onto the mountain. We've learned how the physical properties change in a parcel of air as it increases in elevation, both when it's dry and when it's wet. Next thing we have to focus on is how vegetation actually directly changes with these increasing elevation patterns. So, on all mountains of the world, the vegetation changes with elevation. This occurs due to the changes in temperature and moisture that occur as the air parcels rise up the mountain. So in the Southern Alps, there are 3 basic zones. These different zones are going to be dominated by different plant assemblages, and this term is also known as vertical zonation. So as you move vertically, you're going to see different plant assemblages. So starting at the base of these Southern Alps, you're going to have these shrublands, these more arid climates that are dominated by these low-lying plant communities. As we move up, we have this montane zone dominated by needle leaf forests. Now, these needle leaf forests are more adapted to living in cooler and moister climates. And above that, we have alpine ecosystems. This zone is so cold that trees cannot grow there and instead are dominated by shrubs and non-woody herbaceous plants. Now you can see that there's a space even above the alpine where there's just this cap of ice and snow, and you're not even going to have any plants in some of these high elevation mountains around the world, right? So again, as you move up in elevation, you're seeing totally different plant communities.
Hey guys, so I'm here in the Niagara Gorge and I've been looking at how slope aspect interacts with the vegetation cover. So in this specific part of the Niagara Gorge, we're at Devil's Hole, and in this spot, water has over thousands and thousands of years has worn away at this rock, and we have this gyre here. Now because of it, the shape of this gyre, we actually have on this right hand side is actually a southern facing slope. This left hand side of Devil's Hole is actually a northward facing slope. So you should have read about it in your readings, and again I'm reiterating right now that the north facing slope is definitely going to have a lot less light coming in the northern hemisphere. The southern facing slope is going to have a lot more light throughout the year, so you can actually see, and I'm going to switch lenses in a bit, and we're going to zoom in, and you're actually going to see a whole lot more vegetation on this southern facing slope. So again, when you're on hikes, get a cardinal direction, right? In this part of the lecture, we're going to talk about slope aspect, which is literally the cardinal direction that slope is facing. Northern facing slope versus a southern facing slope. So in terms of slope aspect, I just went over the north facing side and the south facing side. The south facing side is going to have the most incoming solar radiation, and a term that we're going to use in describing this is insolation, incoming solar radiation. So the south facing slope in the northern hemisphere has the highest levels of insolation. The north has the least, and then you have the east and the west. That's going to be slightly less than the southern facing slope, but still not as low as the insolation on the northern facing side.
So I myself found that one example hiking in the Niagara Gorge. I was looking for patterns that I can use in my class, and I'm going on these hikes and I have an idea of what I'm trying to look for, but really I'm really trying to find anything that I could talk about. And I was looking at the map on my phone, and I realized that the only close north and southward facing slopes were going to be in Devil's Hole. So I went there and I did see that pattern. There was more tree cover on that south facing slope. And it's important to note that these patterns are going to vary in every ecosystem that you're in. Like, we're going to look at some other examples that I have that I found pictures at Zora Valley, where the south facing slope has less tree cover. So again, the patterns are going to change in each of these systems. You should know the basics, and the basics basically are that the south facing slopes are going to have higher insolation, they're going to be warmer, and many times they're going to be water limited. So in the system that I stumbled upon was not water limited, and we saw more growth because of that higher photosynthetic activity. A confusing aspect of this, pun intended, is the valley of these mountain faces. So the north side of the valley actually receives more insolation than the south side of the valley, whereas the south side of the mountain receives more insolation than the north side of the mountain. So a little bit confusing, I know. You just have to remember that. So clearly the amount of incoming solar radiation on a slope is influenced by the slope aspect. However, it's also influenced by the slope angle. Now, if the ecosystem is flat, there is no aspect, and all of those sites within that system gets the same amount of incoming solar radiation. However, as the slope increases to an angle of 45 degrees, the amount of insolation increases in the south-facing aspects, like we have touched on, decrease slightly on the eastern and western aspects, and decreases markedly on the north-facing aspects. So that should be some review from that clip that I videotaped. Now, if the slope gets steeper than 45 degrees, the insolation decreases on all slope aspects, including the southern aspect. The angle of 45 degrees is a critical angle because it is about the average angle of the sun in the sky during the whole year. So, as we know, there is a seasonal tilt of the planet, which gives us those seasons, and 45 degrees is the average angle the sun is in during the whole year. During the winter, it has a lower angle, and during the summer, it has a higher angle. So it makes sense that 45 degrees, and if you're, familiar with geometry, 90-degree angle, half of that is a 45-degree angle. So that is the average of incoming solar radiation on a yearly basis. Now, if the slope has the same angle as the sun, then the sunlight will be most direct. The more the slope angle varies from the sun, either by a flatter or steeper, the less insolation the slope will receive. Now, a quick reminder that these interactions of aspect are for places in the northern hemisphere. In the southern hemisphere, those northward facing slopes receive the highest insolation, while the southward facing slopes do not, right? So again, just a quick reminder. So now I'm going to describe the eastern and western aspects in greater detail. So interestingly enough, the western aspect actually is more water limited. So you're going to have different vegetation. You're usually going to have a little bit less vegetation on the a slope that has a western aspect versus a eastern aspect that has that is not as water limited. So a really important thing that we need to know is that the eastern and western aspects actually receive the same amount of insolation. Each day, the same number of photons hit each side of this slope. So why would the western side have a drier slope than the eastern side? And this is because the sun actually rises on the east and sets on the west. So throughout the night and in the early morning, the entire east and western aspects, they are going to have moisture because the sun hasn't been drying them out all throughout the night and especially in the early morning. Now, the plants on the eastern aspect, in the morning they get the sunlight and they have this available moisture. They're going to photosynthesize. They're going to be doing great. Throughout the day, however, the entire slope, both eastern and western aspect, they're going to be drying out throughout the day. So now, as the sun starts to set and starts to hit the western side, that slope is already much more dried out than the eastern slope was, especially in the morning. So you have the sun hitting this western aspect directly in the later parts of the day when the slope is already dried out. This is why you're going to have usually less vegetation on the western side, and there's going to be more water limited. So this isn't as stark a difference between the north and south facing aspects, but we can still see these patterns in nature. So now I want to move into these 4 examples of topographic influences, and starting with this canyon on the western United States of America, you can see that the trees are actually on the northern aspect. So they're on the northern facing side. The south facing side receives so much insolation that the soils are extremely arid and you can only see a few shrubs. There's not many trees on the south facing slope at all. All of these trees in this valley are on the north facing slope. Now here's an example of Zor Valley. So this is a pattern that I saw the opposite in Devil's Hole. Again, this north-facing slope has all these really healthy trees. The south-facing slope actually has different trees. You're going to have trees that are more adapted to drier conditions. You can actually see the leaves are of a different shade on this south-facing slope, and you can definitely see a lot more bare rock. So this southern facing slope receives more sunlight. It is more water limited. Thus, you have different plant assemblages and you have different densities of plants. Now, the third example is this hill in north central Montana. We get to see all these different aspects and all these interactions at work. On this single hill, you get to see that the northern aspect as well as the eastern aspect has the highest amount of vegetation. They are least water limited. On the south and western slopes, we're going to have more insulation, and there's actually this extreme version of this southern aspect here, because you could see this just barren part of the mound where very little vegetation is growing on this southern aspect of this mound. So I think this is a really cool example showing all four cardinal directions at work in relation to slope aspect. And again, I just want to keep reiterating that the different systems are going to interact with aspect differently. So the fourth example is using the Alps in Europe, and by looking at these Alps, we can see that the vegetation zones start at a higher elevation on the south-facing slopes of the mountain compared to the north-facing slopes. So, for example, forests start at 1,200 meters on the warmer and drier south-facing slope, but at only 1,000 meters on the cooler and moister north-facing slope. We can't forget about how latitude influences vegetation type and how latitude actually influences the effect of elevation. At the equator, we have 0 degrees latitude, and as you increase the latitude, you're actually going to decrease in temperature. So at 0 degrees, those places resting on 0 degrees latitude are receiving the highest amounts of insolation annually. At 90 degrees north or south, these places of the planet are receiving the least amount of insolation. They are the coldest, and you barely have any plants growing there. But we have to take these ideas and take that and apply that to how elevation also is at play. So we've already talked about this. We've learned about why temperatures are cooler at higher latitudes. Here is an annual mean temperature of that. And we've been talking a ton about elevation as well. So I'm going to use this example here, looking at northern portion of the Alps, a central portion of the Alps, and then a southern portion of the Alps. So the Alps are still in the northern hemisphere, so the southern Alps are going to be closer to the equator. The northern Alps are going to be further away from the equator. So at higher latitudes, because it's cooler there, the same vegetation zones will occur at lower elevations. For example, if we take a look at this montane zone, it's going to begin at a lower elevation in these northern Alps compared to the central and southern Alps. So in the northern Alps, this occurs at around 400 meters. In the central Alps, this is going to occur at 800 meters, and in the portions of the Alps that are most southern, they're going to occur at 1,000 meters. So we can see this interaction of latitude and how it interacts with these elevation principles. We're going to need to know this term, rain shadow. And a rain shadow is an area of lower precipitation and higher temperature that occurs on the downwind side of the mountain. So we should understand first, because I'm going to be talking about this, that the windward or upwind side of the mountain is the side of the mountain that the wind reaches first. The downwind portion of the mountain is on the other side of that. And the rain shadow occurs on the downwind side of the mountain. At any given elevation, the windward side of the mountain is cooler and moister than it is on the downwind side. The difference in moisture between the windward and downward sides of the mountain is due to the moisture in the air being lost as precipitation on the windward side of the mountain. Remember, as a parcel of air is moving up in elevation, there is less pressure and its temperature goes down, and as its temperature goes down, it is more likely to condensate. And when that happens, water vapor turns into the liquid water, and then you get precipitation. So you get a lot of precipitation on one side, that windward side. So take a look at this figure on the bottom here. Wind coming from the Pacific is moving up in elevation as it reaches the Sierra Nevada mountain range. A lot of that moisture is removed from that wet air from the Pacific as those parcels go through condensation. The air keeps moving, but that water, most of that water actually stays on that windward side. On the other side of the mountain, as that parcel of air keeps moving towards the east, you get this air that has much less water. With air that has much less water, those systems are going to receive much less precipitation, and you're going to have this rain shadow on the downwind side of a mountain range. So I explained how moisture differs in the processes that change the available water in the moving air as it traverses a mountain range. But temperature, the difference in temperature has to do with the dry and wet adiabatic lapse rates. Let's take a look at this example I came up with. Let's assume that a parcel of air is traversing this 10,000 foot mountain amongst the Sierra Nevada mountain range. Let's also assume that for 5,000 feet, so half of the mountain, that parcel of air rises at the dry adiabatic lapse rate. For the other 5,000 feet, it rises at the wet adiabatic lapse rate. So remember, a parcel of air that is rising at its dry adiabatic lapse rate is going to lose 5.5 degrees every 1,000 feet. So we take 5.5, we multiply it by 5, and we come out with 27.5 degrees. So from 80 degrees at 0 degrees altitude, you're going to decrease by 27.5 degrees for that first 5,000 feet, which leads us to this temperature 52.5 degrees. Now, for the next 5,000 feet, it's going to rise at the wet adiabatic lapse rate. And if you remember, the wet adiabatic lapse rate decreases by 2.7 degrees Fahrenheit for every 1,000 feet. So we take this into account. We type in 2.7 times 5 for the 5,000 feet, and the temperature should decrease 13.5 degrees. So that leads us to this temperature at the summit of 39 degrees Fahrenheit. Now this is why the temperature is actually different on the windward side and the downwind side, because most of moisture is completely taken out, so it's not going to decrease the same distance on the downwind side. So here we have these values on the downwind side, and the parcel of air only decreases at the wet adiabatic lapse rate for only 1,000 feet. So we take that 39 degrees, and remember, you're going down in elevation now, so temperature is going to increase. So for 1,000 feet, temperature increases at 2.7 degrees Fahrenheit for every 1,000 feet. Remember, that parcel of air is only decreasing at the wet adiabatic lapse rate for 1,000 feet, so that leads us to 41.7. Now for the remaining 9,000 feet, the parcel of air is going to drop at the dry adiabatic lapse rate. So remember, that's 5.5 degrees per 1,000 feet that it's going to increase. So at the end of this whole process, you actually get much warmer temperatures than were present at 0 feet on the windward side. So for 9,000 feet, the parcel of air is acquiring and gaining temperature at 5.5 degrees per 1,000 feet, and you lead to this really hot temperature on this downwind side. And just one more important thing that we need to realize is that on the downwind side, the reason why that parcel of air only traverses 1,000 feet down the downwind side at the wet adiabatic lapse rate is because most of the moisture was removed from that parcel of air on that windward side via condensation. So the parcel of air has much less water on that downwind side, so it's not going to decrease at the wet adiabatic lapse rate without all that water. So some of the driest places on the planet are actually, and a great example of rain shadow. The Gobi Desert, for example, is in Mongolia, and they're tucked in behind the Himalayas. So this wet and warm moisture from the Indian Ocean is moving north up to these Himalayan mountain range, and literally no water can get over those extremely tall mountains. So on the opposite side, you have extremely dry conditions like the Gobi Desert. In our own country, we have examples. So from California to Nevada, we see this transition in vegetation as a function of elevation, right? So from the wet and warm Pacific weather patterns that move across the coastal range, remember, our coastal redwoods live in this coastal range. There's all this fog coming in, there's all this precipitation. We have this Central Valley, which is then a bit drier. And then as we have this topography, as we have the Sierra Nevada range, we have more water being released. You can see the color, the greenery darkens on this mountain range as water condenses from those parcels of air moving upward, and we have a lot of rain. And on the opposite side, past the Sierra Nevada range, when we lead into Nevada, we have this rain shadow. It's really dry. You're going to have totally different plant assemblages. So we can actually see the rain shadow effect also in the difference in elevation of vegetation zones. So this vertical zonation throughout the Sierra Nevada mountain range. If we take a look at this yellow pine forest, on the windward side, these forests start at 3,000 feet and go up until around 7,000 feet on the windward side. However, on the downwind side, they occur at higher elevations between 7,000 and 9,000 feet. These different vegetation zones occur at different altitudes on either the windward or downwind side. And although this figure on the top right looks like those Alps examples I gave, this vertical zonation is not due to latitude. It is a influence of altitude and these processes that I've gone over. We've talked about these large scale topographic influences on vegetation, but there's also this microtopography that interacts with the vegetation cover. So vernal pools are these small topographic depressions that fill in with water in the spring from snowmelt and become pools. Now, depending how long they flood, they contain either no trees or water tolerant trees. So this is actually a picture from Letchworth Woods. Now, you can see here that the deep parts of the vernal pools contain no trees as seedlings get killed by ponded water. Again, in completely saturated water, there's not oxygen available to the roots. The root material can no longer access stored carbon, and many of these plants, they can get root rot. They can also just die from starvation, not being able to tap in and metabolize their carbon stores. So in the summer, the location of where the vernal pools were is indicated actually by the trees' water-stained trunks. So we can see the level of the vernal pool in this picture on the bottom right with the water-stained bark. That is the level those tree individuals were in. Low areas along streams are flooded less frequently than our vernal pools, but still have water-tolerant species. Sycamore, for example, is a water-tolerant species that's often along streams in the eastern United States. So I actually remember hiking around in our own Letchworth woods on campus, and you did see these vegetation patterns. Cottonwoods also are a riparian species that usually lives along riverbeds, and we had a lot of cottonwoods and sycamore in really saturated habitats. In the next part of the lecture, we're going to focus on how soil influences vegetation patterns. So, spatial variations in both physical and chemical soil properties cause spatial variation in the vegetation patterns. So we're going to focus first on the physical properties of soil and how soil texture actually influences the available water. Now this figure on the right should be reviewed from lecture 4 early on in the semester. On the x-axis, you have these soil textures that decrease in size. So all the way to the left in sand, this soil texture is the coarsest. It's the largest particle size of that soil. As you move to the right, you decrease in the particle size of the soil, and along with that, the attributes of available water change. So in sandy environments, it doesn't matter how much rain those areas get, because sand is so coarse, you have a lot of pore spaces in between those sand particles, and water drains extremely fast, so there isn't a lot of available water. So even if it rains a ton in a really, really sandy environment, it's going to be really dry there. There's not going to be a lot of available water for those plants. Moving into finer textured soils like loams and silt loams, you could see that the available water greatly increases. Those soils can hold on to more water as there's more surface area for water particles to cling on. So it's these intermediate soils that farmers and people in the field of agriculture are trying to attain because of the attributes these particle sizes have. Now, actually, they have some type of mixture, and the most productive soils on the planet, if you remember, have a combination of 20% sand, 20% clay, and 40% of this loamy intermediate soil texture. So these most productive soils actually get the properties of the drainage of sand, so roots don't sit in water, but yet those soils hold on to a lot of moisture, and the clay particles we'll get into next, but we should remember that clay particles have a negative charge and a lot of cations that plants need actually attach to clay, and the plant can then access some of these cations. So again, most productive soils has a mixture, but is dominated by this intermediate soil texture. As we get into pure clay, you actually see that there is a lot of total water, right? The percent of the water can be really high in these clay soils, but the unavailable water actually increases. So available water decreases with these really fine particles because clay has so much surface area, and because clay is a negative charge, it holds on to water molecules so hard that a fine plant root, can't even access many of these water reserves that are attached to clay. So although there's water in these clay soils, it's actually not available to plants, again, because of the negative charge of these clay particles and because of this intense surface area that is clinging on to all of these water molecules. In this example is from Maryland, and these are different tree species that exist in these different Maryland ecosystems, and we could see that these different tree species grow on different soil textures, and this is mainly driven because of how these soil textures influence soil moisture. So 3 of these species we actually have here in Western New York, and we're provided with a useful example. So we have chestnut oak that dominates these drier, sandy conditions. We have tulip poplar that exist in these more moist silt conditions. And then we have sycamore trees that dominate these completely saturated habitats next to streams. The next thing we're going to focus on is the chemical properties of soils. So soils differ in the abundance. They contain different essential soil nutrients. Nitrogen and phosphorus are the 2 main limiting nutrients around the world when it comes to plants. And due to natural selection, species will have evolved to have their own optimum at different levels of the abundance of different nutrients and other soil nutrients. As a result, some species will be more common on nutrient-poor soils, some will be more common on nutrient-rich soils, and others at intermediate soils. This specialization through time is driven by natural selection because we learn that competition is actually a negative interaction. So competition drives these species to actually specialize in their own optimums when it comes to not only nutrients, but their water environment. So natural selection is driven by this species to avoid competition. This figure to the right was from a study that was carried out throughout Vermont and New Hampshire. And in this study, over 1,000 forest plots, 1,249 forest plots to be exact, were looked at. And in those plots, the abundance of species in a stand was compared to an inferred gradient of fertility that reflects the availability of essential soil nutrients. The optimum for a species is the level of that resource at which the species is most abundant at. The theory of natural selection predicts that species should have their optimum at different levels of some resource. So in those 1,249 forest plots, American beech on the bottom left, Fagus grandifolia, had its optimum at a low fertility level. Now, white ash, Fraxinus americana, white pine, Pinus strobus, and sugar maple, Acer saccharum, they have their optimum at a higher fertility level. So we have these three species in the green line having a higher fertility optimum, and only American beech had a lower nutrient optimum. So this goes against this natural selection. However, those three species actually do differ in their optimum condition for moisture. So although it seems like they might overlap, there's this niche overlap in these three species with these green lines. Although they might have a similar nutrient optimum, they have totally different moisture optimums. So sugar maple has an optimum in moister sites, white pine in drier sites, and white ash in this intermediate site. So these species do inhabit different habitats, and the theory of natural selection is still supported. Again, I like this a lot because it might seem like there's this overlap, but in nature, these patterns, sometimes you have to look closer to actually see these patterns. Natural selection drives species to compete less, no matter what, right? Competition is bad, and when it is presented in a system, individuals that are on opposite sides are likely to do better, and that is why there's this directional selection away from competition. So here's this figure that actually looks into their moisture environment. So we have, again, in this purple oval all the way to the left, that's sugar maple having a moisture site. We have Pinus strobus all the way to the right in a much drier soil moisture site, and then we have this white ash in this intermediate site. In the third and final part of this lecture, we're going to look at the emergent landscape. The emergent landscape, the landscape of what we see, is actually the interaction of topography, soils, and disturbance, right? So although we looked at these separately, what we actually see in nature is a combination of these three interactions. So last lecture, we looked at Dr. Chris Larson's study in Wood Buffalo National Park, and we looked at these temporal interactions of fire suppression. We looked at tree rings and how through time we see the frequency of fire changing. So just a little review. If you remember, there is these two parts of these slopes on this figure. And in this first part, in the lower right-hand corner of the actual graph, you have a fire frequency between 1750 and 1860 that was 38 years on average between these fire disturbances. From 1860 on, that fire frequency occurs at a 63-year interval. So the frequency actually decreases in more modern times. Now, their hypothesis was that human fire suppression decreased these fire disturbance frequencies, But they looked at these data, and using these tree ring analyses, they found that fire suppression occurred later on, closer to 1900 and 1950. So they realized that this is due to this climate change, that after this little ice age, there is more available water. When there's more available water, that frequency actually decreased. So we looked at this temporal study. Now we're going to focus on these spatial patterns. We need to remember that Wood Buffalo National Park is made up of half wet lowland forests, and the other half is made up of dry upland forests. So in these two different ecosystems within this national park, the sites show some spatial clustering of recently burned sites and of sites not burned for many years. These patterns reflect the influence of underlying environmental factors. So we have these two patches on this figure. In the purple blob, you have tree individuals that are made up of much older individuals. In the orange plot, you have much younger individuals, showing their relationship with disturbance. Obviously, that orange habitat is going to have younger individuals that experienced more frequent disturbances. So there are underlying patterns that we're going to look into. To better understand this spatial distribution of this emergent landscape, we actually have to look at this patchiness of these individual species. So here is a map showing 4 major tree species, and again, they're showing this spatial clustering. So we're going to actually look at these 4 specific species, starting with the northwestern part of Wood Buffalo National Park. We have these black spruce individuals, and we're going to look at these species and how their soil environment, the soil environment that they actually live in. So these black spruces, they live in these wet clay dominated soils. White spruce, they're dominant on moist margins of rivers and lakes in organic rich soils. Aspen are going to be live on slightly dry silt derived soils, and jack pine dominate on very dry plains of really sandy soils. So we can see that this soil texture actually drives this spatial clustering. Now, these glacial deposits and post-glacial lakes, they actually drive the distribution of these different soil types. So we can actually, this pattern is relative to these ancient processes, as well as these different soil textures were deposited across this land differently. So we looked at how soil texture drives this spatial distribution of these vegetation patterns. Now let's look into how fire interval, this disturbance, drives also this spatial distribution. So let's look at these fire intervals of these 4 species. And we could see in this table on the bottom right, we have white spruce having the longest fire interval at 96 years. We see an intermediate interval for black spruce and the shortest fire interval for jack pine and aspen at 39 years. Now, this is unexpected in 2 ways. Firstly, we have spruce forests are actually more flammable than jack pine forests. Secondly, aspen forests are the least flammable because of these tree species have these broadleaf trees that are packed full of water. So high flammability could lead to higher frequency because those forests would catch fire more easily and burn more quickly. But this is not the pattern that we see. So these least flammable ecosystems actually have a shorter fire interval. So we have to look at this more closely. And when we see the distance of these different species to a water body, remember, half of this national park is made up of these wetlands. So when we take the distance to these different patches to a water body, we can see that the closer these trees are to a body of water, the older those stands actually are. This occurs because water bodies often stop the spread of fire and protect vegetation. Note that variations in topography that cause these water bodies to form. So these interactions are really complex, right? We have topography, we have disturbance, and we have the soil texture culminating into this emergent landscape, the systems that we're actually seeing. The dominant tree species and mean distance to water bodies are made up of this table. So white spruce forests are the closest to these water bodies. Again, white spruce has the longest fire interval. So these white spruce, because they show up closest to these water bodies, there's going to be a lower chance of fire disturbances to run through them. This makes a ton of sense. Jack pine forests, however, are the furthest away of these water bodies at 7.24 kilometers. So this also makes a lot of sense. The further away a tree is from a water body, the more likely they are to be disturbed by these fires. So interestingly enough, we have black spruce and aspen have this intermediate distance to fire. So this relates to fire by selecting species that have a long lifespan, such as white spruce. So remember, the disturbance interval has this strong selective power. If there is a system that experiences a long disturbance, that system is going to select for long-lived species. So the further a forest is from a water body, the more likely it's going to experience fire, and there's this selection towards species that have short lifespans, such as jack pine and aspen. To sum it up, we have these three main topics that we touched on in this lecture and last lecture that drive the emergent landscape. So we have soil texture selecting for different species in both its physical properties, the physical size of that soil that allows different available water, and its chemical properties of its soil in that different nutrients are within different soil types. Both of those chemical and physical properties select for different species. We also have water bodies that modify which species will dominate in a site because the water bodies control fire frequency. Now, again, it's important to note that topography actually drives where these water bodies persist in these ecosystems. So all these interactions are combining into this emergent landscape. Jack pine is going to be mostly soil dependent. It grows better on dry soils than do other species and has thick bark that protects it from surface fires. It is lost from dry sites where there has been a long fire interval because it's close to water bodies. Now this occurs as it has a short lifespan and thus won't live long enough to regenerate itself following a long interval. White spruce is distance dependent, which means it grows better in sites protected from fires by water bodies than do other species. It can grow on silt soils and sites unprotected by water bodies. However, it doesn't become sexually mature and produce seeds until it is 45 years old. So it needs a long disturbance interval, enough for it to mature. Since most sites with silty soils have fire more frequently than that, it cannot regenerate itself in such a short interval. So remember that relations between average fire interval and vegetation in flammability did not make sense because most flammable vegetation had the longest interval between fires. However, the relations between average fire interval and distance to a body of water does explain the differences in fire interval. Thus, in this region, water bodies influence the average fire interval more than does the fuel flammability. Finally, the landscape pattern of what species are present where is thus an emergent property that reflects interactions between soil type, water body distance due to topography, and average fire interval. So I just want to take this time to update the class a little bit. I hope you guys are hanging in there. I hope you guys are taking this as serious as I am. We do have an exam next Thursday, so that is going to be on the 9th of April. So keep up to date with your readings and these lectures. Again, I hope you guys are happy. I hope you guys are healthy. And until next week, I will update our last lecture of this exam section. Have a good weekend.